morning, dear student. Now today we learn the next chapter, Improper Integrals. Myself, Dr. R.S. Damur. I am the Assistant Professor at LD Engineering College of Ahmedabad. Improper Integrals, you learn about the definite integrals and how to solve the definite integrals in your 12th standard and application of this definite integral. But now today we are going to learn this improper integrals. In previous lecture we learned about this indeterminate form, but now we can start with the improper integrals. What is the improper integral, how this improper integrals can be solved, how it's convergent or divergent. It can be applied into the series solution. Whenever you have to find out the series, you can check out the series, is it convergent or divergent, using this improper integrals. So this is my chapter, improper integral, and this is my subtopics for this chapter. First topic is introduction. What is the improper integral? Second topic is improper integral of type 1 and type 2. And third topic is this convergence and divergence of improper integrals. So how you check out this? The integral is proper or improper integral. So only you know that the integral of this type, definite integral. This is known as the definite integral. Whenever you check out this is my limit a to b, and this is known as the domain of this limit, and this fx function fx dx. So this is known as the definite integral, and in your 12th standard you have to learn to solve this definite integral by the fundamental theorem of calculus. A to b fx dx can be written as fb minus fa, where f is the integrand of this. Okay, but what is the condition for this? Okay, definite integral has the domain of integration a to b, so this domain is finite. Okay, and second thing, the function, its range, this function, it is an integrand which is finite on this domain. Okay, so f does not have infinitely discontinuity. This function must be the continuous functions in this domain. So these three things are there. This a and b is finite, this finite domain, this function integrand has a finite domain, and f has a infinitely many discontinuities. It is not contain this, only f is a continuous function. But suppose in practice we may encounter problems that fails to meet one or both of these conditions, which are this. Here we extend our concept of the definite integral to the case where the interval is infinite. So in previous, this is my interval, a to b is interval. So first case is this, we can change this interval to the infinite limit. Second thing, we can extend to this interval, and second thing, if there is a discontinuity in this, then we can absorb this discontinuity in this improper integrals. Say this, in either case the integral is called an improper integral. So what is the improper integral? This. So interval must be infinite, or this integrand has infinitely many discontinuities in this interval. Okay, so this is known as the improper integral. Now say this, where the improper integrals are used. So first use is this, we can find out in your first chapter you find out this convergence and divergence of a series or infinite series. So there you can use the pith test. So this is the first use of this improper integral. Second use is the improper distribution, probability distribution. You can find out the probability distribution using this improper integral. Now say this, the integral for the area under the curve y equal to ln x upon x square from 0 to infinity. Say this, here this domain 0 to infinity. Up till now what we have to do this, there is a to b infinitive, a to b. So there is no infinitive portion are there. So this domain is infinite domain. See this, here the domain is infinite for this function. This is the graph of this y equal to ln x upon x square. See this, here the domain 1 to b and b tends to infinity for this. So this domain is infinite but range of this is fixed. Second thing, the integrand for the area under the curve y equal to 1 upon square root of x between x equal to 0 and x equal to 1. See this, x equal to 0 and x equal to 1, this is the fixed limit, so your definite integral of the type a to b. But what is happen here, y equal to 1 upon square root of x. See this graph, this y equal to 1 upon square root of x. So this 0 to 1 is fixed, okay, but here domain is fixed but range goes to infinite, okay. So this is the another example for this, where the range of the integrand is infinite. So this is two types, domain is infinite or range is infinite. Then this type of integral are known as the improper integrals. Now say this, suppose I can consider the region S under a curve y equal to 1 upon x square above the x-axis and the right of the line x equal to 1. Okay, so I can consider this fx or y equal to 1 upon x square, which is my fx, above the x-axis. So above the x-axis and right of the line x equal to 1. See this, this is my curve y equal to 1 upon x square. And what is the domain? Above the x-axis. So above this line x-axis, okay, and onto the right side of x equal to 1. So this line is x equal to 1 my line, okay, and on the right hand side. So this is my right hand side. Now I want to find out the area for this, okay. So for this, the area of the part S, which is shaded region, this is your region, this region, okay, lies on the left of the line x equal to t is given by, okay, this is limit t tends to infinity at. This is my area, limit t tends to infinity at. So this is nothing but limit t tends to infinity 1 minus 1 upon t, this equal to 1. What is this? The area of the shaded region approaches 1 as t tends to infinity. See this, limit t tends to infinity 1 is the constant term, so taking as it is, and limit t tends to infinity 1 upon t goes to 0. So this is 1 minus 0, and which is equal to 1. So we say that the area of the infinite region S is equal to 1. But here what we have to take this, the limit must be infinite. So now suppose I want to find out this 1 to infinity 1 upon x square. So area bounded by this curve from right hand side of x equal to 1, and this the upper limit tends to infinity. So this can be written as 1 to infinity 1 upon x square dx. So how I write this? I can write this as a limit t tends to infinity. I can take this infinite, t tends to infinite, and I can change the upper limit by t. So limit t tends to infinity 1 is my lower limit, 1 to infinity. So this will be converted into 1 to t, and limit t tends to infinity 1 upon x square dx. Now see this, how this can be written as 1 upon x square. Integration of this term, this is minus 1 upon x, and between the limit 1 to t, okay, so this is minus 1 upon x 1 to t, and you can put down your limit, upper limit minus lower limit, so it can be converted into the form of 1 minus 1 upon t, okay. And in this overview section directly we can find out this limit t tends to infinity as 1 minus 1 upon t goes to 1. So area bounded by this curves equal to 1, okay. So this, how this approaches, suppose this 1 to 2, suppose I can take this region bounded up to 1 to 2, definite integral. So 1 to 2 limit, then I can find out my area as a 1 by 2. But suppose I can extend this 1 to 3, then what is my area? Area is 2 by 3, okay. Same thing, suppose I can extend this to up to 5, okay, upper limit up to 5. So this is 1 to 5, then area bounded by this curve y equal to 1 upon x square, and this x equal to 1 on the right hand side. So this is area is 4 by 5, Same thing, suppose I can extend up to the infinitive. So area is nothing but area equal to 1. So this is the graphical extension of this function 1 upon x square to the limit 1 to 2, 1 to 3, 1 to 5 and then 1 to infinity. Okay. Now improper integral. So you have a basic idea about improper integral. So this integral a to b fx dx is called an improper integral if, what is the first thing? This is one or both limits of integration. This lower limit and upper limit. Okay. This limit or both these limits are infinite. Okay. The first thing is for the improper integral of this is the lower limit and upper limit. One of them or both are the infinite. Then it is called the improper integral. Second thing, the function, this function fx becomes infinite at a point within or at the end point of the interval of integrations. So this fx becomes infinite at this point or the point between a and b. Then this is the improper integral. So this is two limits are infinite or this integrand has infinite values on this point or interior point of this. Then it is called the improper integral. Now say this, how we calculate the improper integral. So there is two types of improper integral. First type improper integrals are this type. Integrals within infinite limits of integrations are improper integrals of type 1. So when this integrand, whenever we find this a or b are infinite or both are infinite, then it is the improper integral of the type 1. Okay, so the first type integral, say this. First thing is this, if fx is a continuous function on a to infinitive, then this a to infinitive fx dx, this is known as the first type improper integral, because here the lower limit is as it is but upper limit tends to infinitive. So a to infinitive fx dx is an improper integral of type 1. Okay. How we calculate this? A to infinitive fx dx. So I can rewrite this as a limit b tends to infinitive. This is a to b fx dx. So now I can find out this definite integral, and putting limit b tends to infinitive, I can find out the integrand a to infinitive fx dx, and which is the improper integral of type 1. Okay. The second form of this, if fx is continuous on minus infinitive to b. Okay, so on the left hand side minus infinitive to b, then how we calculate this? Minus infinitive to b fx dx. So now my upper limit is fixed but lower limit tends to minus infinitive. So to evaluate this type of first type of improper integral, what we have to do this? Now I can take this limit a tends to minus infinitive and a to b fx dx. So first of all I can evaluate this thing a to b fx dx, and taking limit a tends to minus infinitive, whatever may be the values, it is my value of the improper integral of type 1. So this is the type 1 improper integral by replacing this lower limit as a minus infinitive. The third case for this type 1 improper integral, if my both the limit are infinitive. So this is minus infinitive to infinitive. Okay. This is minus infinitive to infinitive. Then what happened? Then see this minus infinitive to infinitive fx dx. Now this type of improper integral, it is the type 1 improper integral, because we can change this upper limit and lower limit by minus infinitive to infinitive. So this is my third case of type 1 improper integrals. Now see this, how I can write this? I can rewrite this minus infinitive to infinitive fx dx as minus infinitive to c plus c to infinitive. So I can divide this interval minus infinitive to infinitive into two parts, minus infinitive to some fixed number fx dx plus fixed number to infinitive fx dx. Here c is any arbitrary real numbers. So this is your first type. Say this minus infinitive to c. So this can be found by limit a tends to infinitive, a tends to minus infinitive, a to c fx dx, and this can be found by limit b tends to infinity c to b fx dx. So this 2 will be converted into your two portions, first 2 minus infinity to c and c to infinity. Okay, so this is 3 case for improper integrals of type 1. Okay, so in each case, if the limit is finite, so there's 3 sub part of this type 1 improper integrals. Each case is the limit is finite and we say the improper integral converges. If the limit is not finite, then we say that, and the limit is not finite, then we say that the improper integral is divergent. And whatever may be the values of this improper integral, it is known as the value of the improper integral. If the limit fails to exist, the improper integrals diverges. Okay. Now say that. Now we can calculate some of the example where we know this idea for improper integral. Suppose I can take this area under the curve y equal to ln x upon x square from x equal to 1 to x equal to infinity. So from x equal to 1 to infinity, ln x square. So what is my area? This is my graph. Y equal to ln x upon x square. Previous example, whatever we have to taking this for this. Which type of this integral? Because my limit is 1 to infinity. So this is type 1 improper integral. Second thing, here the domain is infinite, 1 to b and b tends to infinity, and this is my curve. Okay, now how I evaluate this? So this is area under the curve is given by 1 to infinity ln x upon x square dx. So now see this is my lower limit is fixed and upper limit tends to infinity. So I can rewrite this as a limit t tends to infinity 1 to t. Okay, or taking b as a part, limit b tends to infinity 1 to b ln x upon x square dx. Now say this. So I can take this as a limit b tends to infinity. This is my upper limit, taking this as a b and b tends to infinity. So this integrand will be converted into the integration 1 to b ln x upon x square dx. Now what we have to do this? Now to evaluate this integration ln x upon x square, integration of this part, what we have to do is we can use the integrating by parts. Okay, I can take this integrating by parts. So this can be written as this is. So ln x as it is, integration of this term 1 upon x square. What is the integration of this? Minus 1 upon x. This is my u and v. So you know that integrating by parts, integration of u v dx can be written as u integration of v dx minus integration of du by dx integration of v dx. So I can use this u as it is ln x integration of 1 upon x square, which is minus 1 upon x, minus again integration of this ln x, derivative of this ln x 1 upon x, integration of 1 upon x square minus 1 upon x, and between the limit 1 to b. Okay, so I can simplify this. See this is ln minus 1 upon x 1 to b, 1 upon x minus 1 upon x. So this is minus 1 upon x square minus minus plus 1 upon x square. Okay, and again integration of this term 1 upon x square is nothing but minus 1 upon x. So this is ln minus 1 upon x minus ln x into minus 1 upon x minus 1 upon x. Okay, and whenever I have to put down these two limits, this upper limit minus lower limit. Okay, so upper limit minus lower limit is nothing but minus ln b upon b minus 1 upon b plus 1. See this is the value of this integrand, integration 1 to b ln x upon x square. So it is of the form b. Now what we do this, taking the limit b tends to infinity. So now we are taking this limit b tends to infinity to this. So limit b tends to infinity 1 by b ln x upon x square dx. This can be written as limit b tends to infinity minus ln b upon b minus 1 upon b plus 1. See this. How we calculate this? Now say this ln b tends to infinity, then this 1 upon b goes to 0, 1 is the constant term, so as it is. Now what is about this? Limit b tends to infinity, ln b tends upon b. Say this, b tends to infinity, ln b goes to infinity, this b goes to infinity, so this is infinity upon infinity term. So now recall your previous chapter indeterminate form. So this is infinity upon infinity form, and which is indeterminate form. And for indeterminate form, what we have to use this? We have to use the L'Hopital rule. The L'Hopital rule says that limit x tends to a fx upon gx. If this is of the type 0 upon 0 or infinity upon infinity, then you directly rewrite this limit x tends to a f dash x upon g dash x. So now I can apply the L'Hopital rule for this. See this. Limit b tends to infinity, ln b upon b. Now check out that. This is my fb upon gb. So now derivative of this term, ln b is nothing but minus 1 upon b. Derivative of this term, b is 1. So b multiplied by 1. Okay. Now limit b tends to infinity, minus 1 upon b. So b tends to infinity, 1 upon b tends to 0. So this is equal to 0. So now I can put down these values. So for this, limit b tends to infinity, 1 by 1 b ln x x square dx, integration between this limit, which is equal to 1. So we see that when this limit tends to infinity, but this integrand goes to some fixed limit. So this integral converges and the area has finite value equal to 1. So this is the type 1 integral, improper integral, and we can evaluate type 1 integral using this method. Now say that, suppose I want to evaluate the area under a curve e raised to minus x by 2 in the first quadrant. Okay, say this. This is my curve e raised to minus x by 2 and the first quadrant. So this is your first quadrant. Okay, first, second, third and fourth, but I can only consider this first quadrant. Okay, so in first quadrant, what is the limit? So here the lower limit is 0, but what is the upper limit? 0 to x tends to infinity. So this is nothing but this is 0 to infinity e raised to minus x by 2 dx. Okay, so the area of this curve is given by the integrand 0 to infinity e raised to minus x by 2 dx. Now see that this limit, this is fixed and this goes to infinity. So this is the improper integral of the type 1, because my interval is one of the limit is infinity. So how I rewrite this to evaluate this 0 to infinity e raised to minus x by 2 dx? See this, I can take this b tends to infinity and this is 0 to b e raised to minus x by 2 dx. So this is limit b tends to infinity and this is 0 to b e raised to minus x by 2 dx. Now say this, how I calculate this? You know that integration of e raised to ax is nothing but e raised to ax divided by a. So I can utilize this e raised to minus x by 2. Integration of this term is again e raised to minus x by 2 and divided by this term. So divided by minus 1 by 2. So 2 goes on the numerator. So this is minus twice time e raised to minus x by 2 0 to b. Okay, see this. So I can put down this limit 0 to b. So for this e raised to minus b by 2 into minus 2 minus minus plus and e raised to 0 is 1. So this is equal to 2. Okay, now say that limit b tends to infinity e raised to minus b by 2. Whenever this b tends to infinity, e raised to b tends to infinity, but e raised to minus b tends to 0. So 1 upon e raised to b. So this is tends to 0. So this is nothing but this is equal to 2. So my improper integral 0 to infinity e raised to minus x by 2 dx can be rewrite into this form, and this is nothing but this is equal to 2. Okay, so area bounded by this curve e raised to minus x by 2 into first quadrant is equal to 2, and this is finite limit. So this integral is convergent and area is 2. Now say that suppose in previous two cases what we have to do this, we have to take the one of the limit as a infinite. But suppose two limits are infinite, lower limit and upper limit, then what happen? Okay, so this is minus infinity to infinity. My lower limit goes to minus infinity and upper limit of integrand tends to infinity. So this is the improper integral of type 1, okay, where both the limits tends to infinity. So now to calculate this, I can use this, rewrite this. Okay, so this is minus infinity to infinity 1 upon 1 plus x square dx. So this is minus infinity to 0 and 0 to infinity. So I can break up in this interval into two parts, minus infinity to 0 and 0 to infinity. So to find out this two integral, what I can find out this is separately, same thing I can find out this separately, and whatever may be the answer I can add these two answers. So I got the limit for this. So area bounded by this curve 1 upon 1 plus x square. See this. So minus infinity to 0 1 upon 1 plus x square. How you write this? Minus infinity to 0 1 upon 1 plus x square dx. So this lower limit can be replaced by some fixed number a, and limit a tends to minus infinity a to 0 1 upon 1 plus x square dx. Now to evaluate this integration, a to 0 1 upon 1 plus x square dx, you know about this 1 upon 1 plus x square dx. What is the integration of this term? Okay, just recall this 1 upon 1 plus x square dx, which is nothing but tan inverse x. Say this. And this second portion 0 to infinity 1 upon 1 plus x square dx. How we write this? The upper limit goes to infinity. So this is limit b tends to infinity 0 to b 1 upon 1 plus x square dx. And as we know that we can find out the integration of this term, and put down this two limits, upper limit, lower limit, upper limit, lower limit, and taking the limit as a tends to minus infinity and b tends to infinity. Say this. Suppose I can calculate this term, and I say that the integration of this term 1 plus x square can be written as tan inverse x. So between the limit a to 0. Now check out what is the value of this. Tan inverse upper limit, tan inverse 0. What is the tan inverse 0? Yes, it is 0. And if I put this a tends to minus infinity, so tan inverse minus infinity, so it is nothing but tan inverse 0 upper limit minus tan inverse a, and a tends to minus infinity. So tan inverse 0 goes to 0 and tan inverse minus a goes to minus pi by 2. So this is minus plus pi by 2. So the integration of this first portion minus infinity to 0 1 upon 1 plus x square dx is nothing but this is equal to pi by 2. Now in the similar manner you can find out your second integrand 0 to infinity 1 upon 1 plus x square dx. Clear? As it is similar steps you can go for this, and only the limit is only 0 to b. So what is this? Limit b tends to infinity tan inverse x 0 to b. Now you can check out this upper limit, if tan inverse b and b tends to infinity minus tan inverse 0. So this is b tends to infinity because tan inverse 0 is 0. So the lower limit goes to 0 and upper limit equal to limit b tends to infinity tan inverse b. B tends to infinity, tan inverse infinity. So we know that tan pi by 2 equal to infinity. So this is nothing but this is equal to pi by 2. So this two limits we can find out this for the portion first and second. So this is my second limit. So I can use this minus infinity to infinity 1 upon 1 plus x square. What is this equal to? Minus infinity to 0 1 upon 1 plus x square dx, and 0 to infinity 1 upon 1 plus x square dx. And as earlier we have to calculate this two limits. What is this equal to? This equal to pi by 2, and again this equal to pi by 2. So this is equal to pi. Now see the graph. What is the graph? See this. This is the curve y equal to 1 plus x square, and here x tends to infinity on the right hand side and x tends to minus infinity. So here the limit is minus infinity to infinity. So we can break up into two parts. Here minus infinity to 0 and 0 to infinity. So this portion will be divided into two. Area bounded by this curve, it is the area bounded by this curve and area bounded by this curve. So addition of this 2, here the pi by 2 and here pi by 2, which is equal to pi. So this is the improper integral where the two limits are infinite. Okay, now suppose I can evaluate this. Every time we got this some fixed answer and this integral convergence. Is it possible? Let's say this. Now I can find out this 1 to infinity 1 upon x dx. See this, 1 to infinity 1 upon x dx. So this is the improper integral of type 1 because this upper limit goes to infinity. See this. So I can rewrite this as a limit b tends to infinity 1 to b 1 upon x dx. Now we know that integration of this term 1 upon x. What is the integration of this term? 1 upon x. This goes to log x, log mod x, and limit is 1 to b. Say this. Limit b tends to infinity ln mod x 1 to b. Now I can put down my limits. What is my limit? Limit b tends to infinity ln b minus ln 1. And you know the values of ln 1. What is the values of ln 1? It is 0. So only this limit b tends to infinity ln b. Now say this. When this b tends to infinity, what is this? What is the value of ln b? So ln b also goes to infinity. So the value of this is infinite. So this integrand is not convergent. Okay. Limit does not exist. So the integral diverges. Okay. So there is some values where the integrand is also divergent. If there is some fixed value, then it is convergent. See this. For what value of p, this integral 1 to infinity 1 upon x raised to p. Is it convergence? For what value of p? You can recall that in your series convergence or divergence of series, you can use this, and this is known as the pith series test. Okay, or pith test. Here, infinite series, we can say that it is convergent, divergent, or oscillatory. Okay. Now, this is the use of improper integral to say that about the series 1 upon x raised to p, is it convergent or divergent. Okay. So how we find out this? So to evaluate this 1 to infinity 1 upon x raised to p. So this is my integral, improper integral of type 1 because this upper limit is infinitive. Okay. So upper limit is infinitive, then this is improper integral of type 1. So how I evaluate this? This can be rewrite as a 1 to b 1 upon x raised to p and taking limit b tends to infinity. Say this. This limit b tends to infinity 1 to b integration between this 1 to b 1 upon x raised to p dx. Now say this is x raised to p. So this integration can be written as x raised to minus p, and as you know that integration of x raised to n can be written as x raised to n plus 1 upon n plus 1. So this can be rewrite as a x raised to minus p. So what is the integration of this? Say this, x raised to minus p plus 1 upon minus p plus 1, and this integration limit is 1 to b. Okay. Now I can evaluate this as b tends to infinity. So I can put down my upper limit and lower limit. What is my upper limit? Upper limit x equal to b and lower limit x equal to 1. Okay. So whenever I have to put down this x equal to b, so this is nothing but b to the power minus p plus 1 upon minus p plus 1 minus, whenever I have to put down this x equal to 1, so 1 to the power minus p plus 1 and minus p plus 1. So 1 to the power any power, positive then or negative, so it is always 1. So your lower limit is equal to 1 upon minus p plus 1 and upper limit is b to the power minus p plus 1 divided by minus p plus 1. So this minus p plus 1 is the common factor in denominator. See this. This is my value of this upper limit minus lower limit, and this is the common factor. Now what I have to evaluate this limit as b tends to infinity. So whenever b tends to infinity, what is the value of this bracket? Okay, this bracket there is no change because there is no terms of b. So this as it is 1 upon minus p plus 1. But for this, how I check out this? So for this, I can take this 1 upon 1 minus p outside. So remaining term is this b raised to minus p plus 1. So whenever I can rewrite this into the denominator form, it is nothing but 1 upon b to the power p minus 1, and this factor is common, so this is equal to minus 1. Now say this is fixed number 1 upon 1 minus p. This is fixed, this is 1. It is also constant number. So whenever I can take this limit b tends to infinity, this and this are not changed, but only on this part there is some change, okay, because it is the 1 upon b to the power p minus 1. Okay, now say that what is the value of this? So first case, suppose I can take this p is greater than 1. Clear? If I take this p is greater than 1, it means p minus 1 must be positive term. Okay, so if it is positive term, then 1 upon b to the power p minus 1, and p minus 1 is a positive, so 1 upon b to the power some positive power. So you know that whenever this b tends to infinity, 1 upon b goes to 0, and this is the some positive power, so it also tends to 0. So only the remaining part is this minus 1 upon 1 minus p, and it can be rewrite as a 1 upon p minus 1, taking negative sign here common, and negative sign will be cancelled out. So this goes to 0, and this is 1 upon p minus 1. So what is this? It is the some fixed number. Okay, so whenever I can take this p is greater than 1, it goes to the some fixed number. So this integrand 1 to infinity 1 upon x raised to p, this equal to some fixed limit. And now the second case, which is finite. Okay, we know that it is finite. Second case, suppose I can take this p is less than 1. What is the mean by this? If p is less than 1, then this p minus 1 have a negative power. So this term, this has a negative power, so this goes to numerator. So b tends to infinity, this goes to infinity. So see this limit b tends to infinity 1 upon b to the power p minus 1. P minus 1 is the negative power, so this is negative power, so it goes on the numerator, it becomes positive, and then b tends to infinity, some positive power of b tends to infinity. So what is the limit? Limit b tends to infinity 1 upon 1 minus p, this equal to 1 upon b to the power p minus 1 minus 1, and we say that this is the fixed limit, so as it is, but this p minus 1, it become the negative and goes to the upper side, so it become positive. So this b tends to infinity, this goes to infinity, so whole term goes to infinity. Okay, so which is not finite in case 2. Now what is about the third case? Now we say that if p equal to 1, then this is nothing but 1 to infinity x raised to p dx, and p equal to 1, so this is nothing but 1 upon x dx. So earlier in questions, what we have to find this? For 1 upon x dx, this integral 1 to infinity dx diverges. So this is not finite, and the series is divergent. So we have a 3 case, 1, 2 and 3. If p is less than or equal to 1, then this series divergent, and p is greater than 1, then this series convergent. Okay, so this is known as the pith series test, and by improper integral we can find out this series. So whenever we have to only check out this series is infinite series is convergent or divergent, which is the power of this 1 upon x raised to p, then we can only check out this. If p is greater than 1 directly, then we say that the series is convergent, and if p is less than or equal to 1, the series is divergent. Okay, so in your first chapter infinite series, this most useful test, pith test, to evaluate the infinite series is convergent or divergent. It is of the type 1 upon x raised to p. Let's try to evaluate the following improper integrals. See this. Now see this. Minus infinity to infinity 1 upon e raised to x plus e raised to minus x dx. Okay. Which type this is improper integral? Only type 1, because this limit is minus infinity to infinity. Okay. So this limit is in minus infinity to infinity. So this is the type 1 improper integral. Now to evaluate this, how we saw this? This is minus infinity to infinity, so it can be written as minus infinity to some fixed limit plus some fixed limit to minus infinity. Okay, so we can rewrite this minus infinity to infinity for this. Okay, for this, first of all, we can simplify also. It can be rewritten as e raised to minus x, which is nothing but 1 upon e raised to x, and you can multiply e raised to x onto this side, so this is become e raised to 2x plus 1, and this e raised to x goes to numerator. So this is e raised to x, e raised to 2x plus 1 dx. The slightly modification of this, we will give some good result. Okay, so we can rewrite into this form and we can find out the values of this improper integral using improper integral method. So this can be rewrite as a this term. So this can be divided into two portions, minus infinity to 0 and 0 to infinity. Okay, so whenever I take this minus infinity to 0, okay, then I can take this limit a tends to minus infinity a to 0, and same thing 0 to infinity, then I can take this limit b tends to infinity 0 to b e raised to x upon e raised to 2x plus 1 dx. Clear? So this integral will be divided into two improper integrals, minus infinity to 0 and 0 to infinity, and it can be rewrite as a limit a tends to minus infinity a to 0 e raised to x upon e raised to 2x plus 1 dx plus limit b tends to infinity 0 to b e raised to x upon e raised to 2x plus 1 dx. Now what happened that? See this, how you calculate this integrand, because main thing is this, directly I can calculate this integrand and put down this my upper limit and lower limit, and taking the limit a tends to minus infinity, same thing at here, find out this integral, put down this two limits 0 and b, upper and lower limit, and then taking limit b tends to infinity. Okay, now see this, how you evaluate this. To evaluate this, there is some tricks, which tricks you have to use in 12th standard. Okay, so this integration can be calculating using assumption. Suppose you can take this e raised to x equal to some new variable u. Okay, so e raised to x equal to u, then what is du? E raised to x dx equal to du. Clear? So suppose you can take this e raised to x equal to u, then e raised to 2x is nothing but u square. Clear? So this whole integration can be converted into the 1 upon e raised to 2x. So this is your u square plus 1 du. Okay, so this is nothing but 1 upon u square plus 1 du, and 1 upon u square plus 1. As you know that, what is the integration of this term? Tan inverse u, and again you can put down the values of u, then you get this tan inverse e raised to x. Clear? So this is nothing but tan inverse e raised to x. What again? I repeat that you can take this e raised to x equal to u. Okay, so u equal to e raised to x, then du can be replaced by e raised to x dx. To hold this term, e raised to x dx can be replaced by du. E raised to 2x, e raised to x equal to u, squaring both the sides, so e raised to 2x equal to nothing but u square plus 1. So this whole thing can be converted into 1 upon u square plus 1 dx, and 1 upon u square plus 1 du. Okay, so integration of this 1 upon 1 plus u square is nothing but tan inverse u, but what you put this u equal to e raised to x. So the whole integration can be written as this way, tan inverse e raised to x. Now say this, this can be rewrite into this form. So this can be rewrite into this form, 1 upon e raised to x plus e raised to minus x dx minus infinity to infinity into this form, and we can rewrite into this form. But this whole integrations can be replaced by tan inverse e raised to x. Whole integration can be replaced by tan inverse e raised to x. So only I can put down this limit. Say this. Limit a tends to infinity, tan inverse e raised to x a to 0 plus limit b tends to infinity, tan inverse e raised to x 0 to b. Now see this, hold this a to 0 and 0 to b. Now you can put down your upper limit and lower limit. What do you know that? Tan inverse 0. What is the value of tan inverse 0? Okay, you can recall this tan 0. What is tan 0? Tan 0 equal to 0. Tan inverse 0 is also 0. Clear? So now the upper limit goes to 0 and the lower limit, tan inverse e raised to a. So this is nothing but 0 minus tan inverse e raised to a, and limit a tends to minus infinity. Same thing for this, limit b tends to infinity. What is the upper limit? Tan inverse e raised to b minus tan inverse e raised to 0. E raised to 0 equal to 1, and tan inverse 1 is nothing but pi by 4, because we know that tan pi by 4 equal to 1. Similarly at here, see that e raised to 0, this is also goes to 1. So tan inverse 1 is nothing but pi by 4. Okay, so you can put down this limit. Say this, tan inverse 1 pi by 4 tan inverse of e raised to a plus limit b tends to infinity, tan inverse e raised to b as it is minus pi by 4. Okay, now see this, a tends to minus infinity, so pi by 4 is the fixed value, you can take outside. Tan inverse e raised to a. Okay, now a tends to minus infinity, then e raised to a tends to 0. Okay, and same thing, limit b tends to infinity, tan inverse e raised to b, and b tends to infinity. We know that tan pi by 2 tends to infinity, so this is equal to pi by 2. Okay, so you can put down this values, pi by 4 minus 0 plus this is pi by 2, because tan inverse infinity, which is equal to pi by 2 minus pi by 4. So this is nothing but this pi by 4 positive term, pi by 4 negative term, so only the remaining term is equal to pi by 2. Okay, see friends, in this lecture what we have to do this, we can go for the improper integrals of the type 1, and we can calculate different type of improper integrals. In the next lecture we can go for the improper integral of the type 2. Okay, so we can check out this improper integral of the type 2. How we can check out this improper integral of the type 2 on the base of the type 1. So in the next lecture we can continue our lecture to the improper integral of type 2, and how can we evaluate this improper integral of type 2, and then we can check out that this improper integral is convergent and divergent. There is a test for the convergence and divergence. So there is a limit test, or there is a only comparison test, or there's comparison direct test, direct comparison test, and limit comparison test, and using this you can say that your improper integral is convergent or divergent. Okay, thank you.